And then I'm attempting to continue with the job of educating folks about how awesome DSP is. So let's see, I just want to, folks online, you can hear me again?
Yes, sir, and can see your lecture slides now.
All right, fantastic, thank you. So we were talking about anonymous functions in MATLAB. And so this is how you can define an anonymous function in MATLAB. You can do this like @ symbol, which kind of takes the function name and makes it SQR. So then this is actually defining the function. Whatever x is, you take x as a vector, and every element of x you square. That's what the dot exponent to. That means every element inside of x, if it were a vector or a matrix, will be squared, and then it will return x as the value of the function. So it's sort of a one-liner to declare an actual function. So you can call the function as square of 5, and a will take on the value 25. So you can do this as a step function kind of thing. In MATLAB, how does it look? Let's see, I'd have to kind of recall, but I think what we want to do, the step function is defined that the argument. So I'll do step, that's the name of the function I want to define. It takes in an argument, right? And the argument we'll call n. And then what you do is you have to ask whether or not n is greater than or equal to 1. So you can say n greater than or equal to 0, sorry, n greater than or equal to 0. And that will return, that'll be a Boolean 1, right? That's an expression. So I'm just going to return that expression. It'll either be a 1 or a 0. So I'm going to put a semicolon there, and then let's see, what is it? TF. What did I type? Oh, did I type something wrong? Is my syntax wrong?
Yeah, it needs to be step equals at n.
Yeah, that's right. Thank you. All right. Now I can do step of -1, 0, step of 0. It's 1, step of 100. 1, and we've got it. So now we got, forget heaviside. You can make your own out of an anonymous function in one line. And you can also do that for the delta function, you know, and instead of doing this, you do something like delta equals at n, and then you return n equals 0, you know, like then you're done, right? And so delta of 1 is 0 and delta of 0 is 1. And so you can kind of build up these elementary functions with these tricky little anonymous functions as one-liners. And then you just call them and they work the way that they should, instead of like MATLAB stuff, which is they're very technically accurate, but you have to, you know, you often get into trouble if you don't use them. Okay, so with that said, let's get back to finishing off lecture 5 and transitioning into lecture 6. We need to cover difference equations by the end of lecture today so that you're prepared for both the remainder of the homework and the quiz that we'll have on Thursday. Okay, that's our subject area of interest today. All right, so there's the last few slides here that we want to talk about. And we're getting into the sort of mathematical manipulation at this point. Well, there was one question at the end of last class about this. How do we know that we're restricting our solution? Oh, good grief already. How do we know that we're restricting our solution to n greater than or equal to 1, right? And so towards that end, this product here, when we do its calculation for finding the solution, we look at it in terms of k. But in the final analysis, we have a function of n that comes out. So when we make this decision on limiting the output, we look at how this product here acts on n. And so in this case, you have an n-1 here. So this is going to be there's going to be non-zero output for the values where k is less than or equal to n-1, but then you're going to have this n-1 part that translates to why the output only exists for n greater than or equal to 1. In other words, n is greater than or equal to k plus 1. So when we get the output, it only starts at time index 1 or greater. Okay, and so you just revisit this equation and you look at it in terms of n rather than k to finally get the when the output exists. All right. So properties of LTI systems. And I took my pen away for a second, and that's the cost. So this particular slide talks about the distributive property of convolution. And what that says is that if you have a system that you can represent as two systems in parallel, H1 and H2, and say you took an input signal and you input it both to H1 and to H2, and then you have this, you took as the output the summation of the two systems to get an output signal. That system is completely equivalent to the system where you actually just sum the two systems together, element, or for every value of n, you take the value of the system as the sum of the system value for H1 and H2. You put x of n into that system, and what you get is exactly the same output y. So written down mathematically, it's saying if you take x and convolve it with H1 plus H2, it's equivalent to x convolved with H1 plus x convolved with H2. And that's the distributive property. You can distribute convolution like you do multiplication. Okay, that's a distributive property. Any questions? This is the same exact property what you had in continuous time. Again, cascade, series and cascade. So we did parallel on the last slide. We're doing systems in cascade now. So instead of having two systems in parallel, we have two systems. This should be an H1. We have two systems. Oh, sorry. It should not be an H1. That was actually correct. We have two systems in series. So it goes through H1, then H2. Or if we swap H1 and H2 around. So if we take this one and put it here, and this one and put it there, we get this system here. And so the net effect of these two systems in cascade does not depend upon the order that the systems appear. So x convolved with H1 convolved with H2 is equivalent to x convolved with H2 and then convolved with H1, right? So that is the sort of associative property. It doesn't matter the order in which you associate x's to h's. And there's a combination of sort of the commutative property in there too. It's like when you, since you have H1 and H2 can swap, like convolution doesn't care what order it goes in here. So I could swap H1 with H2 and then distribute, right? So you can see this as sort of also related to the fact that the x and h are interchangeable in the convolution equation in terms of their order. Because if I have H1 convolved with H2, I can interchange their order here and then use the this property of distributivity to kind of prove it the other way around, right? So there's associativity, commutativity, and distributivity has all of these things. Things commute, things distribute, and things you can associate. Like associativity says that if I do draw those parentheses, doesn't matter if I draw the parentheses here or there, you're always going to get the same result in the end. So in a lot of ways, it acts a lot like multiplication, doesn't it? Multiplication also obeys all of these properties. Any questions about that? Now, we can also represent either one of these systems as just a convolution of H1 and H2 and merge the two systems into one. By the way, why might you want to either exercise this property or this property? Why might you want to take two systems and merge them into one using parallelism, say here and here? Or why might you want to take two systems in sequence and merge them to one?
Make the network more efficient?
More efficient is the key, you know, like, so, for example, say that so we know that convolution in general requires n squared operations. You have to, so for every value on the output, you have to do a whole sum on the input, right? And you sum over, say that there were n values in your convolution, right? So if there are n values, you have n multiplies and adds, right? And then there are n values to calculate on the output. So for one value of the output, we have to do a summation of n values. So if there are n values on the output, and then there are n values in the convolution, you have to do n squared operations. So the complexity, the computational complexity of convolution is naively n squared. If you have two convolutions, you have two n squared operations. So if you can merge those two together into one system, you have only n squared operations. So you've reduced the amount of calculation by a factor of 2. You've gone from 2 to 1. This gets used all over the place in AI and ML, convolutional neural networks. It's part of the title of how they work. Convolution is an intrinsic part of it. And convolution is the source of billions of dollars of industry. When you talk about the AI industry, much of that industry is based on the fundamental concept of convolution as realized in a convolutional neural net, a CNN. So if you hear AI, ML, deep learning, all of this stuff, the fundamental underlying mechanism by which much of the inference occurs is using convolution. Pretty important. Same principles apply to systems and sequence. Okay, so here's a system, and I don't know how this happened. Here's a system. This is the forward difference system. So this is our system. We have a forward difference system followed by a one sample delay. And so the forward difference system is this system. The one sample delay, you can represent this as the system delta of n minus 1. Why can I do that? If I take x of n, some arbitrary signal, and I convolve it with delta of n minus 1, what do I get as output? Fantastic, by the sifting property. And knowing the sifting property is one of your fundamental tools to success in this class. So you use it a lot. You use it on the FIR, IIR convolution, and you use it over and over and over again. It's just one of those things to really have available to you. So here we have this as a system, which is our forward difference system. We're convolving it with delta of n minus 1. That means to take every one of these functions and shift it to the right in time or by one sample, which means that delta of n plus 1 becomes delta of n. And this minus delta of n becomes minus delta of n minus 1. And all of a sudden, the forward difference system becomes the backward difference system, right? We're taking the current value and subtracting the previous value, which is what this system does. And how can we show that? Let's give it an arbitrary input. If you take x of n and convolve it with this, with this system, h of n, what is the difference equation we get? So I'm going to write y of n is equal to that. We get what? X of n minus x of n minus 1. And so when you subtract x of n minus x of n minus 1, you're getting the difference or the slope of the line that connects the two sequential values, which is how we talk about derivatives. It's the slope of the line. And since we only have values at integers, this is the closest measurements that we have. So we're just taking the slope as it's available to us on two sequential values and saying that the slope of those values is in fact the output, which is the discrete difference of the function. Let's see. These are cascaded systems, and so when we did this, we just simplified that system. Right. This was a system forward difference. This is another system, a one sample delay. We convolved the two systems, and we got this system, and then we used that system. So we just practiced the idea of cascaded system and how to collapse those two things, right? This would have taken more operations, and we simplified it. So it's an example of not only, how to work this stuff, but how this cascaded stuff might work as well. Any questions about that before I go on? Okay. Properties of systems. So now that we've done properties, right? There's stability, the causality, linearity, time invariance, memory lists. We've done these properties. And we did them, we always wrote them as input-output relations. Like some of the things that you might recall, like we wrote like y of n is equal to tangent of x of n, right? This is a system. The system itself takes the value of the input, x of n, and takes the tangent of it and puts that out on the output, y of n. And so this was our representation of the system at that time. So now that we have a new representation of a system in terms of the impulse response, h of n, we can write down all of these properties in terms of h of n and do analysis on h of n rather than on a x and y equation, because these are different ways of representing systems. So we can still evaluate these properties on these different representations. So when we think of the representation of the system as the impulse response or the sample domain representation, A system is stable if the sum, the absolute sum of all the values of H is finite. So if you can extract the impulse response and then figure out if its absolute sum is finite, then you will know if the system is stable. So even if you were to look at the system and say, I don't know how to tell if that system is stable, if you can get H of n out and then evaluate this property, that's another way to solve that problem. Okay, and so, and then this stuff down here just to prove, indicates why that is true. So it writes that, first of all, if we have to realize that as soon as I write this down, I don't even have to tell you whether or not the system is linear or time invariant. Why is that? Well, it's written as H of n. H of n is part of the convolution equation, and all convolutions are representations for linear and time invariant systems. So as soon as I tell you a system is represented as H of n, if I were to ask you if that system is linear and time invariant, do you need to do the only thing you have to do is say yes, because it's represented, like I might even give you H of n is equal to 5 and ask you if it's a linear or time invariant system. It is. It's represented as H of n. It's almost a trick question, but it's not. It's actually, you have to know that. It's like this is a thing. This is like the fact that any system that's represented as an impulse response is intrinsically linear and time invariant is something you need to be aware of. Now, further, if you're able to get H, if you have H and you want to know whether it's stable, well, you can look as to whether or not it's absolutely summable. Is its sum of all the magnitude of its values less than infinity? If that property is satisfied, it is stable. And this is why, there's an inequality here. We write down the convolution equation, and then we say that that's less than the magnitude. So the magnitude of this whole thing is less than the magnitude of each of the individual parts multiplied. And this half of that, so if X is bounded, then this itself has to be bounded. Therefore, if this sum on H is bounded, the whole thing is bounded. That's why that property is true. Does that make sense? So you could do it as a mathematical proof, but I'm just gonna hit it. It's kind of. Okay, so we have this, this is the convolution equation, and what we're doing is we're just measuring the magnitude of the convolution equation, right? Now, the property that we're trying to show is bounded input, bounded output, right? And so that means that X of n, every one of these values, X of n minus K, is bounded because of the BI, the bounded input part. So every one of these values here, I could say is bounded by some value beta X. And I could just put a constant in there. And then I have everyone, so this sum is going to be, however many terms in beta X, right? But then we have to look at whether or not this itself is bounded. And if this is not bounded, we find that the whole sum isn't bounded. Yeah. Yeah. This means that this thing here is taking the magnitude or the absolute. They call this from a mathematical perspective. Do you remember absolutely integrable? Like they used to say something like this. This was the definition of absolutely integrable. So it kind of goes to absolutely summable. Yes, absolutely. In fact, they are the same. And it's kind of that's a tricky statement, but let me show you why they're the same. So the magnitude of a complex number is z, right? It's the square root of its real part. So if z were equal to a plus j times b, the magnitude of it will be the square root of a squared plus b squared, right? And so if z is purely real, this ends up being the square root of a squared, which is equal to the absolute value of a, right? So it is sort of, so for real values, it's automatically the absolute value, right? And for complex values, we refer to it as the magnitude, but in mathematics, they just refer to it as absolutely summable without the notion of what kind of a number it is. But that redundancy of the absolute value to the complex magnitude is something that sometimes students don't get exposed to. I'm just kind of pointing it out.
It's also called the modulus, right?
Yep, it's also called the modulus. Yeah, there's a there's so many terminologies that one can use, but yes. So if X is bounded, that means that the magnitude of X is less than this. So then we can take it out of this sum because it's a constant and it shows up in the front here. So then we just have to focus on whether this is bounded. That's the mathematical proof.
And how do we,
So that's, I think you were asking about that, right? Yeah. Does that make sense?
Makes more sense. I need to work with that a little bit.
Yeah, just think, don't even, so X of n minus K, we can think of this as a function that might depend on like the position n minus K. But if it's all less than some value beta, beta is no longer a function of the index n or K. So it's just a constant. We're just going to put a constant above all the values and use that constant. So because this does not depend on K itself, we can move it out in front of the sum. That's how it gets here. And then, you know, you have to so y of n, the output will be bounded by this bound, which is finite. We've already established bounded input. So by this number times this number. And the only way that this product can be infinite is if this second number is infinite, because we already have a finite number bx. And so that's what gives us this criteria for stability. That sum has to be finite. Okay. Checking system stability. Okay, ideal delay system. What is h of n? It's this delta. So this is the system. Can we extract h of n out of this? Well, how do you get x of n minus n naught? Well, you can write it as x of n convolved with delta of n minus n naught. It's another, do I know the sifting property kind of question. Then this here is h of n. And so h of n, in fact, only has one value. So it's sum from minus infinity to infinity. It's in fact very finite. It's 1. Is it stable? It is stable because its sum of the magnitude of all of its values is less than infinity. In fact, it has only one value. It has magnitude 1. So the sum would evaluate to 1 instead of infinity. Because it evaluates to 1, which is less than infinity, the system is stable. Forward difference system. Well, this is a, in fact, like instead of even like, so we look at the forward difference system, the backward difference system. Let me just generalize this. If you have an FIR system, an FIR system is a list of numbers that are all finite in value and finite in length. How could you bound such a list of numbers if you wanted to find some number that all of those numbers was less than?
you make it less of the sum, right?
You can make it less than the sum. You can even make it less than the max. Like take the max and add 1 or epsilon or whatever. So all of your values are less than this, and then just plug that value in. Right? And we get back to this property right here, right? So I want to say this, if you have any FIR system consisting of finite values, it has to be stable because the sum of its value, sum of its values is finite, as you were saying. And that would be the test. Or you could take, for every one of those values, the maximum of all the values. And that sum would also be finite, which is kind of like I was working from the bounded perspective. Let's bound it and then sum, right? And whatever. Doesn't matter. Either perspective is correct. Any questions?
Yeah, so what would be an example of something that's not bounded?
Well, let's do h of n is equal to say u of n. All right, so what is this? So what is the sum from k goes from minus infinity sum to positive infinity of u of n? So we want to simplify the sum first, well, the magnitude of u of n rather. We simplify the sum. Where does the sum actually start? What's the first non-zero value of the sum? So this is actually the sum from k equals 0 to infinity. And what value does u evaluate to for these u of k evaluate to for these values of k? 1. So it's a sum from 0 to infinity of the number 1. Is that finite?
So it's gonna keep on adding 1 to itself for all infinite numbers. So it'll be infinite, right? IFR or IFR.
That is infinite.
Right.
You even if this were epsilon, If even if this were like the closest number, like think of the closest number that you can get to zero. If you sum that up an infinite number of times, doesn't matter how close you are to zero. Doesn't care. Math doesn't care. You can't get close to zero and not be zero. You have to be zero if you expect to have a sum of numbers whose magnitude converges to zero, or they have to cancel each other out. Like you can have an alternating series. Maybe you can do sum of -1 to the n from k equals 0 to infinity. And that's going to jump up and down. It's going to cancel itself out every time. Every odd number is going to be negative. Every even number is going to be positive. So it's going to be bounded, this sum. Right? It'll be 1 for 0, 0 for 1, or and so forth. It's going to. So you look at these things, you know, they might not be as simple as you have to think about them. You have to think about what's going on with these equations. It's not just a formulaic kind of thing. You just look at it, do some analysis, and then move forward. Any other questions before I go?
So would that mean that the delta function is finite?
The delta function is certainly so this here is a stable. So this is a stable system.
Oh, yeah. So
This one here is stable. Any FIR function, any FIR filter that consists of finite values will be a stable system.
would that mean?
Could I give you an FIR value that has an infinite value? Could I give you a filter H that has the value infinity? Like, can I write this down? H of n is equal to infinity for n equal to 0. I just did it. I wrote it down. I can write down systems that are unstable. Is it still linear and time invariant? Sure, but it's not stable, not at all. Like this is a valid system. I can write this down. I can get this crazy. You know, it's just math, right? Okay. Checking system stability. So we have a little bit of like how do you go about it? You basically could go and compute this sum. That's the operational, the key operational part of it. So here's an accumulator system. All right, and what we do is we actually figure out, in this case, this is what the impulse response of such a system is. And the way that we look at it is we look at this we look at the sum, and we have to decide whether the sum is finite. And in fact, the sum is in fact a step function, so we already know whether or not this is finite or not. We know that it's not finite, so we know if this is unstable. We just kind of verified it on our previous slide as sort of an example of an unstable system. Now the moving average system, on the other hand, which is represented like this is the impulse response of the moving average system. It starts from minus m1 to m2, and it's these delta functions. And so when you sum this up, this is what the sums come to. So the value of this system is 1 over m1 plus m2 plus 1 for any value of n that's in between m1 and m2, but 0 otherwise. So every value of the impulse response, like its magnitude, is finite. So this is a stable system. If x of n is bounded, then the average of the x of n's are also bounded, whether it's a moving average or otherwise. That makes sense, right?
So we can't just look at the signal and tell if something is bounded in or bounded outward just by looking at the signal, right? So if the signal has a whole bunch of deltas in it, can we just assume that that's going to be finite?
Well, what if I did this? If I wrote infinity times delta of n, which is exactly what I just, that's another way of I could write this that way, right? You just have to make sure that the magnitude of all of the coefficients, are finite if it's an FIR filter. So your process will work as long as all of the coefficients of the FIR filter are finite. If it has feedback, it will be like some kind of an IIR system. So it'll be an infinite sum of some sort, like this. In which case you have to make sure that infinite sum, we have to do this, like if remember something like a to the n, like if you end up with something that looks like this, sum n equals 0 to infinity a to the n. What will that converge to? First of all, there's a criteria. Does anyone remember the criteria on A?
It has to be less than the absolute value. Oh yeah, absolute, that's the point.
If the magnitude of A is less than 1, this converges to what value?
To a finite number.
1 over 1 minus A, which is a finite number. But that's exactly what you have to test for stability on infinite IRR systems. You're going to end up usually with a sum that looks something like this. And if the value A is less than 1, then it will end up being finite, because that's, you know, that's what the sum comes out to when that's a finite sum. But if A were the magnitude, what if the magnitude of the A in this sum were 1 or larger?
You know,
It's going to explode, which implies what about stability?
that is not.
Then it's not stable. So when you start analyzing infinite impulse response systems, represented where h of n is some kind of infinite length thing, you have to be very careful to look at the nature of the sum. Here in this case, you might think of this as just like 1 to the n as an a to the n thing, right? By the way, u of n, 1 to the n is always 1. So you can just write u of n as 1 to the n, you know, for all values of n greater than or equal to 0, and apply this and find that it's going to be infinite as well, right? It's like just, I don't even know why I'm talking about that, but it's just like another way. This thing comes up all the time. This equation with a to the n comes up all the time, and you can even use it maybe in unanticipated ways. All right. So if it's an FIR filter, as long as all of its values are finite, it's stable. If it's an IAR filter, you've got to sit down there and do analysis. Find out if the sum, the infinite sum that's part of that IAR filter, is going to result in a finite sum. Usually that involves applying your geometric series. Causality. All right, so if you have a causal system, the only thing that requires on H is that it has 0 values for any value of n that's less than 0. If H of n is defined for any value of n that's less than 0, it is not causal. Let me give you an example. H of n is equal to delta of n plus 1. If I do x of n convolved with h of n, what do I get? X of n plus 1, right? And that would be equal to y of n. Now we've already looked at the system. Y of n is equal to x of n plus 1. What was that? Is that causal? Y of 0 depends on x of 1. That means the current value at 0 depends on a value that hasn't of the next value of x. Is that a causal relation? No. So we took an example. H, this value of h occurs at n equal to minus 1. It has a value at n equals negative 1. And the system is not causal. So this rule about whether or not, so if there's exists a value of h for any value of n that's less than 0, you're going to have a system that's not causal. Clear? If the values of h that exist are restricted to n equal to 0 or positive, is it causal? Yes. That's the fundamental rule. Okay.
Belong to the late input, or to the late input output.
Yeah, so if we did the h of n is equal to delta of n minus n naught, so n minus n naught, and I restrict n naught only to, so n naught is something greater than 0, so that is that causal? Yeah. It is causal because h of n is restricted to only having values at 0. That's when n naught is equal to 0, or for some value of n that's greater than 0. Make sense? Now, I can also say that for any FIR filter that's consisting of only values that are deltas shifted to the right, that's also true because it's true for this value. So if I take a bunch of systems that are all sums of delta functions and they're all shifted to the right, that's also causal, right? Because it's just now the system is a combination of exactly the same system that we just said here. And we said that any such system like this, I could take a sum of these delta functions, n minus k. K goes from 0 to n naught, and you know, and that's has to be causal, right? If I write h of n in this way, it's just a bunch of the properties above, but all of those properties are satisfied for any finite n naught, right? Now, if n naught is not finite, things change because now we no longer have a finite impulse response filter. We have an infinite. All right. Causality. But again, even if it were infinite, it'd be right-sided. So in causality, it would be fine. Just wouldn't be stable. So this is where we're going to end off our discussion here. We already know that this is linear and time invariant. I guess if we wanted to talk about memory lists, if H of n is memory list if it's only defined at n equal to 0. That's the memory list property. It has to be only defined at n equals to 0. If it's defined at any other value of n, it is not memory list. Make sense? All right, having said that, we're going to transition out of this. We have we're going to get into the next lecture topic. We're really going to focus on getting you the technical skills necessary to solve difference equations. Because difference equations are both on your homework and on your quiz on Thursday. All right. So this is our second lecture in the lecture series consisting of 3 different topic areas. And we're talking about 3 different ways to represent a linear and time invariant system. Representation 1, sample domain representation, H of n, the impulse response. We just talked all about H of n. That last lecture was all about H of n and the things that you can do with it, which is convolution in 3 different flavors and system property analysis in the various flavors that we just covered in lecture. This lecture is all about difference equations, linear, constant, coefficient, difference equations. So this is a difference equation lecture. This is the second way to represent a linear and time invariant system. There are 3 representations that we deal with. There's the impulse response, the difference equation, and then the discrete time Fourier transform, well, there's the Fourier space. These are the 3 things that we'll study prior to the midterm exam. It's chapter 2.5 and 2, sections 2.5 and 2.6 from chapter 2 of the textbook. And of course, we're already working on this and we'll have this shortly. In fact, even on Thursday, inadvertently. There is a subject of eigenfunctions as well that we want to talk about, but really the technical skill we want is difference equations. We're focusing on that for this lecture. Okay, so we have the same slide. We're still representing a linear time. It's a representation of a system. It operates on input values, creates output values. You can represent it mathematically as T, it's something that operates on the input, or it's a block diagram. Also as T, but we just draw a box around it and call it T and kind of put a graph where the information flows from left to right. So how do we write a difference equation? So this is going to look a lot like a differential equation. At least I'd like you to think about that. You're going to be invoking the same skill set to solve it. So a linear constant coefficient difference equation has a general form of a bunch of shifted versions of y multiplied by a bunch of coefficients, dk, is equal to a bunch of shifted versions of x multiplied by a bunch of coefficients, pk. So we do the same kind of thing that we did in the past. Is like, remember when we solved for the block diagram of y, we had a coefficient we divided through by that first coefficient of y. We're doing the same thing, but now we're doing it in a much more general form. And so you might remember that we had something like, I don't know if this is the right equation, but it might be 3y of n plus 2y of n minus 1 is equal to x of n. This is a difference equation, right? I've got 2 terms in dk, one for y of n, one for y of n minus 1. And I've got a 1 for x of n, so p0 is actually 1, right? Those are my actual values for these coefficients. This one here, this is d0. This coefficient here, this is d1, and this one here, this is p1, right? So this is a difference equation, fits into this model here. And when we did the block diagram for it, we did it sort of purposefully incorrectly. And then we said, oh, well, we have to divide through by this 3 so that we have y of n on the right side and we can calculate all the right amplification terms to make the information flow from left to right. And so when we did that, we got y of n is equal to, and then we had 1/3 x of n minus 2/3 y of n minus 1. We did something like that. So we're doing the same thing here, but just in a mathematical form. This equation that you see right here is exactly the same operation, but we're just calling d0. We're calling this coefficient here d0, and we're doing it for any version of a difference equation where that coefficient is just the variable d0. So that's what's going on here. And then we're more generally saying that, hey, so we take all the other terms and why they have this negative sign, right? Just like this term here has a negative sign because I moved it to the other side of the equation. And we're saying, hey, since this is all difference equations, this is another valid way of writing it where I just simplify it. And so I have y of n and then everything else, all the other terms are on the other side of the equation. Okay, and so when we look at these equations, we have some terminology to establish. The first thing is, what is the order of a difference equation? So in the order, when we talk about the order of a differential equation, how do we determine the order of a differential equation? It's the highest, yeah, it's the highest value of the derivative. So analogous to that, it's the highest shift or the highest time delay. So it's essentially it's the if you think about the backward difference as x of n minus x of n minus 1, we say that that's a difference, a first order difference. It's like dn, right? So that's a first order. And what's the highest shift in that? 1, right? Because you have an x of n minus x of n minus 1. So the shift there is 1. The order of that equation is 1. If you continue that analogy for this difference equation out to arbitrary shifts, the order becomes the maximum shift in the equation, either in y, which would be differentials in y, or in x. So you're basically looking for the maximum shift. So here's a difference equation. What is the order of that difference equation? Yep, it's the maximum shift. That's how to answer such a question. You're looking for the maximum shift. That's this value here. This is shifted by 2. So the order of this difference equation is 2. Now, we can also go about taking, we can get the impulse response. And so the way that we get the impulse response for a difference equation is we just use the definition of the impulse response. So if you have, so a difference equation is another representation for a linear time invariant system. And we know that if we have a difference equation, it must have an h of n, right? Now, there's one caveat to that. Difference equations with 0 initial conditions are linear and time invariant, right? And think of them like difference equations and differential equations are almost exactly the same. In order to solve them, you need a certain criteria. So you need the equation itself. But if you were to solve a differential equation, say it was first order, what else do you need to solve it? The initial conditions. How many initial conditions do you need? It depends on the order. So you need as many conditions as the order of the equation. So if you have a first order equation, you need 1 initial condition. If you have a second order differential equation, you need 2 initial conditions. That does not change for difference equations. You want to solve a first order difference equation, you need 1 initial condition. You want to solve a second order difference equation, you need 2 initial conditions. Now, I want to say something very clear. Difference equations are linear and time invariant if their initial conditions are 0. If their initial conditions are not 0, they are not linear and time, more specifically, they're not time invariant. Why is that? Initial conditions are defined. Like say I say y of -1, the output at time -1 is equal to 5. If I shift the difference equation, that initial condition does not shift. So the solution becomes different if I shift the difference equation or not. So it's no longer time invariant. And so that's the reason why non-zero valued difference equations are not time invariant. The initial conditions don't shift. Right.
That means that y, so you had so that means that y -1 should equal 0.
Yeah, well, see, yeah, exactly. Only if the initial conditions are all 0, well, then the system is already implicitly defined to have value 0 wherever it's not defined. So those initial conditions implicitly shift because of the definition of how the system works. Like if you put 0 in, 0 gets out. Yeah, you'll be able to solve the system in both circumstances. If you have the initial conditions, you can solve it. Now, if the initial conditions are 0, it's linear and time invariant. If the initial conditions are non-zero, it is not LTI because the initial condition doesn't shift. Like you can shift the entire difference equation, the time at which the initial conditions are defined to have a non-zero value don't shift with the output. It's like the system has already been excited, and if you shift the equation, its response will change and be different because the whole system is behaving at a different, as if it were excited at a different time, but the values of the initial conditions don't change, don't move with that. They still occur at, say, -1. Does everyone understand that idea? Yeah, like the initial conditions don't get delayed, like when you do that, and because when you do the experiment, and because those initial conditions don't shift with the actual definition of the system, it becomes a time varying system. Okay, so let's go ahead and do this by inference. So we take this equation here, and we put let's see, we want to calculate the impulse response. So what do? We let the input be the delta function. So when we let the input be the delta function, we get this as our equation, right? And so the delta function has been substituted for x of n here and here, right? And so then we can actually start solving for values of y. Y of 0 is equal to alpha times 0. So we're gonna, this assumes, by the way, we have alpha times y of n minus 1. So we actually need the initial condition y of -1 is equal to 0, and we're applying that condition right here. That's how we get that 0, right? So we're saying there's an initial condition of y of -1 equals to 0, and that's what we're putting in right here. Because we're taking y of 0, that's equal to alpha times y of -1. And we're saying y of -1 is equal to 0 right there. Then we take delta of 0 plus beta delta of n minus 2. Well, delta of 0 is 1, so this ends up being 1. This is 0, so this is 0, and this is 0. So we just get delta of 0 as the output. Okay, next line, y of 1. Well, it's alpha times y of 0, which had the value 1. So this value ends up going here. Times delta of 1, and that ends up being 0. Beta times delta of -1, that's 0. So that means you have alpha times 1, which is alpha coming up. Why? You could continue the process, and it just becomes recursive. So this alpha goes here, right? And then this should be alpha times alpha, not alpha times 2. Delta of 2 is 0. Beta times delta of 0 is actually beta, so we get alpha squared plus beta. So there's actually a typo on the slide right here. It should be not 2, but alpha. I'm going to put a little mark for myself to correct the slide there. And so we get alpha squared plus beta on output. And then if we continue, we see that we get alpha times alpha squared plus beta, alpha times alpha squared plus beta. And more generally, so we get this recursive process. If we wanted to, we could write in a general form. We know that alpha squared plus beta is this term that everything's multiplying. And this was alpha times that. So this would be, so when n has the value of 3, we're multiplying by alpha. So we could do alpha to the n minus 2. And if n were 3, n minus 2 would be 1. And if we write it like this, this is actually the general form of y. We can sort of write it down by inference, and it only starts times 0. So we have to multiply it by u of n. And so this is the general form of the output of that difference equation by inference, by just kind of iterating it, kind of drawing out, looking at the pattern that evolves, and then generalizing that pattern by induction. So as method 1 of solving a difference equation, the induction method. And it's just a matter of plugging values in. So in a pinch, if the other methods don't work, you can always try the method of induction, which is just plug and chug. But it is both time consuming, and at the very end, you have to know how to generalize this pattern to some kind of equation, right? So it's kind of can be difficult. But I also want you to, we do this as the first example, so you understand how difference equations operate, like how they work. They're recursive. Like if you have y of n as a function of other y's, then you end up having this recursive relationship. And it also gives you, a possible technique for solution, like this inductive technique. Okay. Yeah.
So the initial condition for this problem minus one is equal to 0 and y of 0 is equal to 1.
So in this particular case, we didn't actually solve for the entire solution to this. We actually only solved for the impulse response. So this would be the homogeneous solution to the differential equation. So it's only sort of half of this total solution. So we said, look, to get the system impulse response, so we're actually calculating h of n. And h of n actually corresponds to what if you remember your differential equations theory, this is the homogeneous solution. This is the solution as if the input were equal to 0, except for having the delta function at the origin, right? That is what the homogeneous response is for a differential equation. And this is the analogy of that in difference equations.
Right.
So it's not the total solution. Like this is y of n is equal to h of n.
So how will we
And
know-
that's because x of n was equal to the delta function.
So how will we know that y minus 1 is equal to 0 is not equal to us in this particular example?
So in the homogeneous solution, you always set the,
Oh, the initial value.
you set the input to 0. Yeah, like,
Yeah, okay.
so it's assumed to be a system at rest. Yeah, so difference equations actually are going to be a more challenge. There's a lot that comes, just like differential equations. Like you've got 2171, and then you see it in circuits 2, 2112. You see it again, 2254. And then you see it yet again in 3111. And you probably, depending on where you go, what you're, whether you're a computer engineer or electrical engineer, you see it in other places too. But you're all differential equation experts. You've seen it. At least you had a whole course on it with 2171. You saw it in 2254 as a whole section. You saw it in 2112 in practice in AC circuits. And then you practice it again in 3111 when you solve differential equations as they relate to systems. So I'm trying to use all of that expertise and trying not to build new bridges in the world of discrete domain. We're just trying to use all of that stuff and reuse it here. So yeah, there's, you could think of that this is a whole thing, but it's really not, because we're just solving differential equations, but they happen to be called difference equations, and they're in the discrete domain, and we just plow forward, right? We just use all of our skills. We got tons, you guys got crazy skills on differential equations. So we're gonna use all that. Okay. Schematic representations. Well, and this shows you how to draw a schematic. What I really want to focus on is how you're going to solve a differential equation, the difference equation. So we're going to really just I'm going to skip all this and come back over it. I want you guys to have the skills to solve a difference equation, and we have 10 minutes to do it. So that's going to happen right now. All right, techniques for solution. You want to solve a difference equation, you break down your solution into a homogeneous part and a particular part, just like you do in differential equations. Now, for difference equations, just like in differential equations, we presume that we know the solution. What's the solution? Well, if it's a first order difference equation, we say it's e to the x or e to the t or whatever times some constant, right? And then we solve for the constants, the method of unknown coefficients, and you solve for the coefficient. If it's quadratic, we say it's e times some trigonometric function. And we already know the solution. So we do the same thing, but the presumed solution is different. The form of our solution is lambda to the n. It's not e to the n. It's some unknown number lambda. We plug that, just like we do in differential equations, we plug our known solution, lambda to the n, into the difference equation, and we get our characteristic polynomial coming out. Then we have to solve for the roots of this characteristic polynomial, which is the values of lambda. Right? So if it's a first order characteristic polynomial, the value of lambda is d1 over d0, right? And that's assuming that you have d0 y of n plus d1 y of n minus 1 plus d2 y of n minus 2. So I'm actually writing down the general solution to any second order difference equation in terms of d0, d1, and d2, right? If it's written like this as a difference equation, you have to be careful about make sure your d has the right sign. But the answer is d1 over d0. That's the value of lambda. If you have a first order difference equation, the value of lambda, if you have a second order difference equation, is that you have two values for lambda. And this equation is just solving the quadratic equation for this system where you have D0 is A, D1 is B, and D2 is C. And this is the equation that you get out of that. Now, when you have that, you'll have the homogeneous solution. You'll have half of your actual difference equation solution. And you write it down as some unknown coefficient alpha 1 times the known value lambda 1 that you'll either get from here or here is the only value, and your known value of lambda 2 times some unknown coefficient alpha 2. And you will have half of your solution, the homogeneous half. The general solution is the sum of the homogeneous and the particular. This is just the homogeneous solution. So next you find the particular solution, right? So the solution, so this technique to solve is multiple slides. So first thing is you know that it's summed into two parts. The second step is to get the homogeneous solution. So that's what we just did. You basically, you have to solve for this constant lambda. Then write down the solution as alpha 1, some value you don't know, times either lambda 1 if it's just first order, or lambda 1 to alpha 2, lambda 2 for a second order system. Then we have to get the particular solution. The process for that is that we assume that the output is of the same form as the input. Okay, and here's an example. If the input were a step function, so if x of n were k times u of n, the particular solution would have the form beta times u of n, some different constant times the input function. So if the x of n was some sine with a frequency omega 0 and phase phi, it's going to have this some sine but unknown magnitude and different unknown phase, same frequency. Then what you do is you take your particular solution and plug it back into the equation, and you solve finally for the unknown constants. So you'll solve for beta in this case, or you would solve for alpha and theta in the other case. You solve for the things that define the particular solution. So at the end of this, you'll have a homogeneous solution, lambda, an unknown coefficient alpha for each of your lambdas, and a particular solution with all of its values known. Your final step is to add the particular and the homogeneous solution, and then use the initial conditions to solve for the value of alpha that you do not know. Okay, let's do an example. All right, this is a difference equation. What is its order? Second, we have a delay of 2 here. Second order difference in y. What are the value of D0, D1, and D2? 1 for D0, 1 for D1, and -6 for D2, right? And where the input is defined to be 8 times the step function, that's going to be used for finding our particular solution. We need to have 2 initial conditions defined, so we can solve for the form of it, but we're going to be left with alpha 1 and alpha 2 unknown unless we have initial conditions, right? So let's go forward. In all of its steps, we let the homogeneous solution is given by assuming y of n is equal to lambda to the n, and we let the input equal 0, just like we do in differential equations, right? The input has value 0, we have differentials in y, and we solve. We plug lambda to the n in to the equation, so we get lambda to the n for y of n plus lambda to the n minus n for y of n minus 1. -6 lambda to the n minus 2 is equal to 0. You get this equation in lambdas. Now this equation, this part, a lot of people kind of get confused. We're going to factor out lambda to the n minus 2, and it kind of reverses the order of things a little bit, right? So that means that lambda to the n is now lambda squared, because you multiply in the 2's, they cancel, you get lambda to the n back, right? So I factor out this lambda to the n minus 2, and I get this quadratic characteristic polynomial in lambda. So this is the characteristic polynomial. I can factor this. And so I factor it, and I get the roots. This is the factorization, and this is the roots. Or you can just apply the quadratic formula as I gave it to you originally, and or you can just go back to this slide and apply this directly, and you'll get lambda 1 and lambda 2. but I'm doing out all of the steps here, right? So now we get lambda 1 is -3, and we can write down the solution. This is the homogeneous solution. It's alpha 1, something I don't know, times lambda 1, which is, I'm going to take lambda 1 as this one, -3. So times lambda 1 to the n. And alpha 2 times lambda 2 to the n. And that's the homogeneous solution. Now I need to find the particular solution. So the form of x is 8 times the step function. So the output will have the same form as the input. That's an unknown constant times the step function. And we plug that in. We plug that in and we get, well, if the output is of the form beta times u of n, y of n is beta times u of n, that first one. Y of n minus 10, y of n minus 1 is beta times u of n minus 1. Minus 6 y of n is minus 6 beta u of n minus 2. And then, of course, that's equal to x of n, which is 8 u of n. And now we have an equation in all step functions. Now I'm going to do something here. I'm going to say, I'm going to let this solution apply for n is greater than or equal to 2. In which case, this and this and this and this, they are all equal to what? All these step functions for n greater than or equal to 2 have the value 1. And that's the key thing to this next step. That's why they all disappear. Now you have beta plus beta minus 6 beta equals 8. We can solve for beta. Beta is minus 2. Now that we solve for beta, we know the particular form of y. Y is minus 2 u of n, restricted to the fact that n is greater than or equal to 2. That's going to come back to us because when we write down our solution will only apply for when n is greater than or equal to 2. There will be a different value that comes out of this system at n equals 0 and at n equals to 1. But this is going to be universally correct for all values of n greater than or equal to 2. Yes. Yes, so I did that in order to simplify the equation here. And so I want to solve for all, so I want all of these step functions to evaluate to 1. And the only circumstance under which that situation is true is when the value of n is greater than or equal to 2. Now, having said that, the solution I'm going to get as a result of that is only valid for values of n greater than or equal to 2. A separate solution would be necessary for n equals 1, in which case it would not include that term with the 6, right? It would not include this. And a separate solution would be warranted for n equal to 0, right? But what I'll typically be asking you is for what is this thing at n equals 7 or something like that. So so generally speaking, you're looking for what is the steady state response. The steady state response of the system is for values of n greater than or equal to 2. Yes. You can solve for beta for n equal to 0, n equal to 1, and n equal to 2. The betas will be different, and your final solution will be different. But in fact, this system actually has only 2 values that are not generally solved. So we're solving for all values of n. So we're solving for an infinite number of values when we do this. So our values of the system for n equal to 2 or greater, there is a value for the system at 1 and 0. We are not actually calculating those values, but they can be calculated by simply dropping that terms off of this. Yes.
Those 2 values that are solved for,
they're not, they're the transient response. It's a sort of a non-steady state response. So like you'll get this, the system needs 2 values to come to stability before it goes to steady state. And see, these are the values that it transitions through before it comes to steady state. So this is sort of the steady state, like they call it in differential equations, they also call it something like the steady state response. And so they're typically solving for steady state, right? But there is a transient response, and I'm telling you that it exists. The steady system will transition. Systems don't instantly come to steady state. They have to transition. And here, I'm telling you exactly that that's the case. And in this case, there's 2 values that it needs to transition from its at-rest response through its, this is called the transient response, to its steady state response. Yes, you had a question?
4, we let the homogeneous equal lambda 3n.
Yeah.
And but then on slide 12, it says in general that the homogeneous solution equal alpha to lambda.
So when you're doing the homogeneous solution, y of n is equal to lambda to the n. That's the only correct thing. If there's something, so here is, what slide are you?
Slide 12 is true above.
12. This is slide 12. Yeah, so this is the unknown coefficient. This alpha here is in fact the same alpha that we get right here. Right, so that's still there. Yeah. So it's they're consistent and correct. Yeah, there's no problem there. Practice these methods for solving your own difference equations in the homework, and ask questions if you have them, and come to office hours if you need assistance. I'm going to post. I made a video of solving difference equations last semester. I think I have available. I'll make that available to you so you can see me kind of do it for some equation, for some example.
The homework is gonna be.
The homework is due on Thursday. Yeah, it's due where it's going to be due as it's already due, and the quiz will be where it's already defined.
But I mean, we haven't finished this lecture, so will we be able to solve all the homework?
You can solve the homeworks. You need this skill, right? This skill that I just told you about is what you need to solve the difference equation problems.
Oh, man, I
So-
was hoping that we did more.
Well, no, this is what you need. This is it. It's all happening.
Oh, really? I think the COVID virus is running rampant on campus.
Yeah, the robotics is yeah, I just saw Conrad today, robotics.
Yeah,
He
yeah.
told me robotics is online.
Yeah, it's online, because apparently a lot of
Yes,
them.
it is. Yes. Everything he's saying is, I saw Conrad today virtually, and he said all of that, yeah.
Yeah.